Today we are going to establish the equilibrium condition for a domain where we have vapor state and liquid state of a pure component is going to be at equilibrium. In the previous video we have established the mathematical identities that led us to the conclusion that for an equilibrium between two different states of aggregation of a pure fluid, the pressures should be equal, their temperatures should be equal, and their molar Gibbs free energies are going to be equal. Then we discussed the possibility of stability, and we have noted that in this PV curve of a constant temperature line, the system is stable as long as the variation of pressure with respect to volume is less than 0. And beyond this point, we have an unstable region. We have also touched upon the point that the areas under these domains, I will call alpha and beta, the areas under the alpha and beta domains should be equal for the estimation of the pressure that is going to have the equilibrium vapor pressure of the fluid at the indicated temperature. We have arrived to this point by starting from a closed system first and second law analysis. First we wrote the energy balance, then the entropy balance, and also we invoked the second law relative to the entropy generation. And under the conditions where U and V are constant, where U and V are constant, we noticed that heat should be 0. Heat dropped out of this equation, rendering ds over dt to be equal to entropy generation. And then we noticed that the ds over dt was equal to entropy generation, which should be greater than or equal to 0. All right, so the equilibrium condition where we have the entropy as the constraint led us to the point that under constant internal energy and constant volume, entropy should be maximized. Entropy to be maximized requires that ds over dt is equal to 0 at the equilibrium point, and its second derivative, d square s, I'm not going to write dt for the reasons that will become obvious later, d square s should be less than 0, and this is going to be our stability criterion. And the stability criterion applies to the condition where our constraints are internal energy and volume of the system are constant. Now, given this, let us remember that the conceptual equilibrium condition, that the pressure variation with respect to volume has to be less than 0. So let's just make this a little bit clear this should be less than 0, right, is going to be evident from d square s to be less than 0. But before we go to the algebra of this problem, let us see what other constraints lead us to equilibrium conditions. Earlier, in the thermodynamics 1 videos, we have derived the shaft work required the shaft work required for a gas confined in a piston and cylinder arrangement differed when we had different constraints. And this time, we are not going to discuss it from the point of view of the shaft work, but we are going to discuss from the point of view of a closed system. Our first set of constraints were internal energy and volume. Now let us have a second set of constraints of what would happen if our constraints are temperature and volume. In order to keep the system at a constant temperature, we need to provide a heat exchange. As a result, keeping a system at constant temperature requires a heat exchange which can be reflected as T times entropy. So let us extract Q term from the entropy balance as T multiplied by ds over dt minus S generated. And substitute this into the energy balance. T ds over dt plus S dot generated minus P dV over dt. Right? So when we rearrange this equation, we see that d over dt u minus t s is equal to S generated. Between those two equations, we have done two things. Number one, volume is constant. We dropped this out of the equation. Temperature is constant. Therefore, we put this temperature into the derivative sign. So the final equation is as follows. So this expression was labeled as the Helmholtz free energy. And now we have a second constraint. Temperature and volume, leading to the maximization, minimization of the Helmholtz free energy. All right. This should be minus, this should be minus S generated. If entropy generation has to be greater than or equal to 0, minus S generation has to be less than or equal to 0. As a result, we have a Helmholtz free energy minimum if our system approaches equilibrium under constant temperature and volume constraints. All right? So this is the second set of constraints. Now let us have a third set of constraints. What if we have temperature and pressure constant? we begin from the same set of equations. Energy balance, entropy balance, the second law. Temperature and volume constraints led to this equation by dropping this term. But here I'm going to keep the pressure constant along with temperature. Therefore, I don't have to drop this term out of this equation. As a result, I can start from here. du over dt is equal to T ds over dt minus S generation minus P dB over dt. Let us separate the domains so that we are not confused. And of course, here we have T times S generated. This is T times S generated. All right. So temperature is constant. I put this temperature into the derivative sign. Pressure is constant. I put this pressure into this derivative sign and I rearrange. I have d over dt u minus ts plus pv is equal to minus T times S generated. All right. And this term has already been defined as the Gibbs free energy. So we have a new set of equations under the conditions of constant temperature and pressure. We arrive at an equilibrium state where the Gibbs free energy is minimum. So those are important aspects of the equilibrium conditions. All right. Our equilibria has to go through entropy maximization under internal energy and volume, constant approach to equilibrium. Under temperature and pressure constant approach to equilibrium, we will minimize Gibbs free energy. Under constant temperature and volume approach to equilibrium, we will minimize the Helmholtz free energy. So this Gibbs free energy minimum is an important constraint where we will apply that rule to find the equilibrium state, where we have an equilibrium state at constant pressure and constant temperature. Of course, Gibbs free energy is also constant at its minimum. Right? If we go beyond this point in the liquid state, or if we go beyond this point in the vapor state, we will have a condition of metastability. It is not stable, it is beyond stable, that we will maintain a vapor state, it is going to be stable, but metastable. True stable equilibrium will require that in those two states, the Gibbs free energy of the fluids in the liquid state and the vapor state are going to be equal. So when we plot the Gibbs free energy of the Gibbs free energy of a fluid at constant pressure for a liquid this side, or for a vapor we will find a point of cross-section that they are equal, and for this pressure this is going to be our equilibrium temperature. All right, so this plot is another perspective of the same information plotted in the Gibbs free energy temperature domain. Now let's discuss this second derivative of entropy to be equal to 0. In the meantime, notice that I have corrected a mistake of labeling of these two curves. The curve that goes under is vapor, and the other one is liquid, which was labeled in the opposing way by just a momentary forgetfulness. So let's start from d square s being less than 0 as a stability condition. Now I'm not going to bring the whole entropy function into the discussion. Please follow from the Sandler's chapter 7 derivations to find out that in order to have this, we need to have n times del square s over del u square at constant v and n should be less than 0. In order to have this, we will start from the internal energy. Let's just have our internal energy function here. They are derived from those two equations, but let's have it at our proximity for convenience. And if we extract entropy from this equation, we're going to have 1 over t du plus p over t dv. So let's see what the first and second derivatives look like. This is going to be n times del over del u at constant v and n times del s over del u at constant v and n. Now let's see if a volume, and of course let's add g dn into these equations minus g dn, just to establish the fact that number of moles are going to change between those two states of aggregation. So del s over del u at constant v and n. If v is constant, this term is going to be eliminated. If n is constant, this term is going to be eliminated. Del s over del u, under those conditions, is going to be 1 over t. So now n del over del U, 1 over T at constant V and N. All right, let's take this derivative. This is going to be minus N over T squared times del T over del U at constant V and N. All right, and remember, this was heat capacity at constant volume. Wrap it up. Minus N over T squared C sub V is going to be less than 0. Right? This is our starting point. We arrived at some physical parameters leading to the stability condition. So N is the number of moles, it's a positive quantity. Temperature is always in the absolute scale and it's a positive quantity. Remaining, the only parameter is the heat capacity. If this group with a minus in front is less than 0, then eliminating minus is going to make this greater than 0, or heat capacity is going to be greater than 0. All right? So this is an important stability criterion. All right? This is going to give us the thermal stability condition. The other stability condition requires a little bit more algebra. Just take my word for it. The other stability criterion is del P over del V is going to be less than 0. When it is 0, it's the boundary. And if it is greater than 0, our fluid state is not stable. So we have two stability criteria. One is this. The other one is del P over del V at constant T and N. It's going to be less than 0. They're both coming from d squared S being less than 0. And I strongly recommend for going through the algebra. Now let us derive the fundamental equation of equality of Gibbs free energies and the equation of the fugacity. So again, we will start from the basis of the G being equal to minus S dt plus V dp. All right, if you don't remember, you can go back to the earlier videos where we derived those equalities. dG, total molar Gibbs free energy, is equal to minus SdT plus VdP. Now, remember, we are looking for the condition of equilibrium on a constant temperature curve. If temperature is constant, this term drops out. So our Gibbs free energy is V dP. All right? So you're going to work around this Gibbs free energy function. Now we are going to integrate this between two pressure states, P1 and P2. All right? So we're going to have Gibbs free energy after integration. This is going to be Gibbs free energy at a constant temperature T and P2 minus Gibbs free energy at the same constant temperature and P1 should be equal to integral V dP between P1 and P2. If my fluid behaves like an ideal gas, I can write the same expression but I can use the ideal gas law to substitute for the specific volume. So now I have two different expressions. One is for an ideal gas, one is for a real fluid. What I will do, I will subtract this from that to have an expression for the difference between the real fluid from its ideal counterpart. Minus G of T and P1 minus G of ideal gas T P1 should be equal to integral V minus RT over P dP. All right? When I generalize this expression for the difference of the Gibbs free energy between a real fluid and its ideal counterpart, I can write this as G minus G ideal gas, right? The limits of this one, this are from P1 to P2. If I'm going to limit this to the difference of the Gibbs free energies of a real fluid from that of its ideal gas counterpart, my expression will look like an integral from 0, where the fluids behave like an ideal gas, and P, now it's an arbitrary pressure, V minus RT over P dP. All right? So I'm going to take two giant leaps forward. One giant leap is going to normalize this with respect to the temperature divided by RT. And the second, I will just take the exponential and I will call this fugacity. So, seeing everything in writing, we have divided G minus G ideal gas, the difference between the Gibbs free energy of the real fluid from that of its ideal counterpart, divided by RT, and RT has the energy units, this has the energy units, and as a result, this ratio is dimensionless. We have divided the other side with RT to render this dimensionless, and we have taken the exponential. We call this group as a dimensionless group. This is the fugacity coefficient. We represent it by the Greek letter phi. Greek letter phi is the ratio of fugacity divided by pressure. If we take the natural logarithm of the fugacity coefficient, we get an expression of 1 over RT, integral from 0 to P, V minus RT over P dP. And if our fluid is close to an ideal behavior, V is going to have an ideal behavior. This group is going to be 0, and therefore fugacity coefficient is going to be 1, and therefore fugacity of the fluid close to the ideal gas domains is going to be equal to the pressure of the gas. Now we are going to take care of this integrand. Now remember, van der Waals equation of state was explicit in terms of volume, implicit in terms of pressure. So it is difficult to extract this dP term from an equation of state. Instead, if we can make a variable change of this from a pressure integrand to a volume integrand, we are going to handle the mathematics a little bit more easily. So let us start from a derivative of PV. This is going to be equal to P dV plus V dP. In other words, dP is equal to 1 over V dPV minus P over V dV. So I will do some algebra here. All right? Remember, the compressibility factor was, and of course, all of these volumes are intensive volumes. Z was equal to PV over RT. So I can just introduce an RT multiplier between numerator and the denominator in order to have a Z integrand. We have dP is equal to 1 over V. I can multiply this by P, divide it by P. I can multiply this by RT, divide it by RT. And I have dPV minus P over V dV. So I can have an integrand of PV over RT, P over Z, dPV over RT times dZ minus P over V dV. All right. So when I bring this integrand and use it here for this function, my integral looks something like this. 1 over RT integral 0 to P V minus RT over P. Now instead of dP, I will bring this integrand times dP, P over Z dZ minus P over V dB. I will leave the algebra to you. I will write the final expression for the fugacity coefficient for your reference. So the algebra of this new integrand lead us to a new expression of the fugacity coefficient as 1 over RT. Now our integrand is dV, and our integration limits now starting from volume from infinity going to the volume that corresponds to this pressure. Our function is RT over V minus P times dV. And of course, from these factors, we obtained an ln z plus z minus 1 after the integration of the z integral. So this is the final expression of the fugacity coefficient, which we will use to estimate the equilibrium between two states. And remember how we arrived at here. We have started deriving a function for the Gibbs free energy at constant temperature. We have taken the temperature parameter out of the discussion. Remaining volume pressure relationship is used to arrive at a function which is to be integrated with respect to pressure. All right. But then we noticed that integrating with respect to pressure is difficult, and we needed to make a change of integrand. We switched the independent variable from pressure to compressibility factor and volume, and our final function looks like this. Now this final function is an implicit function of the Gibbs free energy. As a result, instead of the equalities of the Gibbs free energies, which requires us to go through the entropy parameters, we have an equation here which represents the fugacity coefficient of the fluid, and that equation can be estimated using an equation of state explicit in volume. For example, I can substitute van der Waals equation of state here to estimate the fugacities. And now I can say that fugacity coefficient in state 1 is equal to fugacity coefficient in state 2 instead of Gibbs free energy, or I can say fugacity of phase 1 is equal to fugacity of phase 2. And now having one equation of state, which is explicit in temperature, pressure, and volume, which is a function of temperature, pressure, and volume, allows me to estimate a vapor-liquid equilibrium. So we are going to practice this. We are going to practice derivation of the stability criteria, and we are going to use this function to estimate vapor-liquid equilibrium in pure fluids, and then it is going to be very useful in estimating vapor-liquid equilibrium of multi-component systems. So let's apply the equality of the Gibbs free energies to a specific application. So Gibbs free energy is V dP minus S dt. On one phase, V dP minus S dt on the other phase. All right? So we are going to group pressure terms together and group temperature terms together. V1 minus V2 dP is equal to S1 minus S2 dt. So we have del P over del T at constant Gibbs free energy is equal to S2 S1 minus S2 divided by V1 minus V2. Now, remember our concern that entropy is not a easily accessible parameter, so we are going to describe entropy in terms of the enthalpies. Again, we are going to invoke the equalities of the Gibbs free energy, but this time we are going to write this as H1 minus T S1, and Gibbs free energy in phase 2 will be H2 minus T S2, and the difference will be 0 here, equalities of the Gibbs free energies. That is going to be equal to H1 minus H2 minus T S1 minus S2. And from here, we will derive S1 minus S2 as H1 minus H2 divided by the temperature. We will substitute it in here as 1 over T H1 minus H2 divided by V1 minus V2. All right? This is the Clapeyron equation. Now, let us make a couple of assumptions and approximations. If my phase 1 is the liquid, phase 2 is the vapor, this is going to be delta H vaporization. All right, phase 1 is liquid, phase 2 is vapor. Phase 1 is a liquid and phase 2 is vapor. And remember, the specific volumes of the liquids corresponding to their vapor counterparts are 3 orders of magnitude smaller. So with that, I can easily drop this first term, and I'm left with minus V2. I will take this minus 2 up. I have 1 over T. I will make one leap of faith here, and I will make the assumption that in the vapor state, my fluid behaves like an ideal gas, so I will substitute the ideal gas law here. V is equal to RT over P. All right? And that T term drops. So my Clapeyron equation, I'll just move to the total derivative now. dP over dt is going to be equal to, no, I'm sorry, they don't cancel out. It's 1 over T squared the minus in front, delta H vaporization divided by R over P. I'm going to group pressure terms and temperature terms together. I will have dP over P to be equal to minus delta H vaporization dt over T square on the side. So if I integrate between P1 and P2, and if I integrate between T1 and T2, I have a neat equation which is called Clausius-Clapeyron equation. And this equation allows me to do two things. First, if I measure the vapor pressure of a fluid at two different temperatures, I can estimate its heat of vaporization. If I can measure the vapor pressure of a fluid at two different temperatures, I can estimate its enthalpy of vaporization. If I have the enthalpy of vaporization of the fluid, if I know this, and if it is independent of temperature, of course, or pressure, and if I know the vapor pressure of the fluid at one temperature, I can estimate the vapor pressure of that fluid at any temperature. All right? So this is a useful, convenient equation that we use in making vapor pressure estimations. So this wraps up the 7th chapter of Sandler.